So I have always wanted to understand about the real-time messaging system. Like, how do these apps are able to send the messages from one place to another so quickly at such a large scale? And of course, it's not just sending one message from here to there, right? It cannot be a simple API call because at scale, to build systems, there must be some challenges. And yeah, today I want to spend like next few minutes on understanding this particular thing. Like, how do messages get from one place to another super fast? And let's I will be using my friend AI as usual to understand in depth about each of the topics and kind of try to explain to you along the side as well. So listen to everything that I mentioned in this video very carefully and let's get started. So what I'm just asking it right now is to behave like a senior software engineer. And first of all, as we do, and first of all, let's get started with the challenges that are there in building such a system. And then we would understand. So first of all, let's start with understanding what are the challenges to this almost real-time communication thing. So yeah, let's hit chat. So yeah, this is kind of my question. So to start with, I just want to know what are the challenges of sending so many messages from one place to other for so many users at the same time, right? So and on this tab, I will be taking some notes. Here we have the timer that's going on right now. Okay. So as I am seeing the first challenge, that is the C10M problem as they call it. But the real-time communication essentially happens over WebSockets. If you do not understand WebSockets, let me know. I will make a separate video over it. But it's a continuous connection between the server and the client kind of thing. For now, you can assume that. And then we need to have, if 10 million users are using your app at the same time, then you need to maintain 10 million of those connections with your server at at any time, right? So yeah, and this is specifically hard because essentially you need to balance the traffic properly to to handle memory, to load balance all of them properly, and handle the spikes essentially. Okay, we will dive into the solution of this in a little while, but okay, let's move to the second problem. Okay, the second problem is as follows. Let me try to explain. So it's more on how do you deliver message from one place to another, from one user to another. The problem is especially exaggerated when the user sends a message to the group. So if you're posting message with a group of large number of people, then you must send that message to each member of that group. That's the point of this entire group, and that is difficult because the users can be in different locations connected to different servers. And yeah, and you have to handle such spikes again. This that like one message is sent to 50,000 group people, then you need to handle that spike properly without burning your CPUs out, right? So that is another problem that is super nice to understand. And then the latency challenge, and this gets exaggerated with the fact that there are different users can still be at very far apart locations. So you need, yeah, that it seems that the latency is around 50 milliseconds globally. So so in that case, yes, setting up those WebSocket connections and with all the security layers and routing the traffic can add some delay. So what they are trying to tell is that we need to do something smart about it as well. And then finally we have the data consistency and reliability problem. So when you are working with distributed systems, you might come across this data consistency and the cap theorem part essentially. So Yeah, ensuring that once, what the users expect is that messages to be arriving in order and never be lost. So one approach of that can be exactly once delivery, which is something like the receiver gets the message one message exactly once, but that can be extremely expensive and slow. So they resort to at least once, so that okay, the user receives the message at least once. I do not know what's really going on behind the scenes, but yeah, this can be a problem of ensuring in the real time that okay, the message is delivered and it is not lost, and they are delivered in order. Given that these are very nice challenges that we should also consider, that the network flakiness, so the message should still go through in order when the network is not connected, or the network is flaky. And what happens if message 1 takes a slower route? So you need like sequencing mechanisms as well. And yeah, basically if your user has sent the message but the receiver has turned off the internet or something like that, then how do you ensure that the message is delivered? And then there are more other things like user is typing and read receipts, so a lot of metadata. And I think one of the problems that is not mentioned here is how do you optimize, like keeping taking care of all these, we need to optimize for the battery life as well, app performance, because if your app consumes too much battery on the device, then it's not something users would like. So let me just summarize the notes that we have here, right? So one, we had how to keep so many users connected at the same time, right? Then we have the fan out problem, how to handle fan out of messages in large groups. Ooh. How to keep latency low. And then how to ensure ordered delivery of messages at least once. And then yeah, I would skip this metadata part because it can be discussed in later on, but how to do all this while utilizing battery efficiently. Okay, so we have 5 challenges that I think would give us a lot more information about this thing. So let's try to dive into this part, right? How to keep so many users connected at the same time, right? uh, and one question is, are the users connected even when they are not using the app? How to handle the case users are not when users are not using the app, right? So they are not using the app, so they are still connected or not. And yeah, I think this is what I want to understand. So the first thing that I'm realizing here is that they are mentioning about two paths. One is the hot path, one is the cold path, which is for online users or the active users, and one is for when the users are not using. There is some asynchronous signaling that we will, let's say, talk about later on. So I would just keep it in the note. So hot path and cold path, and then there is this thing. So if you have ever tried to build a WebSocket based application, you would have noticed that there are significant performance degradations as soon as you start to have 10, or like if you are a college student, just try to build one very basic app at very low scales as well, you would start to observe the degradation. So how do you handle 50,000 users or even more? That is a super interesting question to dive into. So what they are saying, it's not the CPU, it's the memory management and OS resource limits. Okay. So the standard web architectures don't work, and connection gateway layer is the keyword I think we were looking for. So what is this connection gateway layer? Okay. Okay, this seems a little bit more interesting as well. Like there is a dedicated fleet of servers whose entire job is just to maintain those connections and put the data from one place to other. Apparently they don't authenticate, they don't read from database, they just ferry the bytes from the socket onto an internal message bus and from internal to externals. Interesting. So just a layer that handle the connections. Okay. The runtime. Standard web servers. Okay, so there is something that here we need. Okay, there are so many technical terms that are coming here that can be confusing. So but I won't be able to cover all of them because of the limited time. So my suggestion is that you just keep note of these wordings and try to understand more about them by yourself. But essentially what they're saying is that we cannot use thread per request model where, okay, if you have a request, you create a thread, you process that, it would use too much of the space and doesn't scale really well. So we need to use some asynchronous and non-blocking IO mechanisms. Okay, which seems to be very scalable. So what they are doing to achieve that is Erlang. Okay, I do not understand what is Erlang. So what is it? Oh, it's a programming language. Creating a low latency, distributed and fault tolerant system. Okay, I didn't know such a language existed, but okay. This seems to be used by WhatsApp. So, okay, to handle concurrency. Yeah, okay. So The thing is that they are using a specific language to help build such a system which can handle concurrency. And then there are Go routines as well, and then there is Netty Java framework. So interesting. And then Java option is Netty. You can of course learn more about this by yourself. And then there is OS tuning, kernel level strategy. Linux is not ready for 500k connections on the machine. We have to tune the kernel. Every open socket is a file in Unix. We must aggressively raise the limit to allow millions of open files. TCP keep alive. We need to aggressively tune TCP keep alive packets to detect dead PIs. If a mobile device drives into a tunnel, their phone won't be send a polite disconnect packet. Okay, the server needs to figure out a mobile user drives into the tunnel, disconnect packet you won't get. So the server need to figure out the connection is dead and free up the resources, otherwise you leak the memory until the server crashes. Okay, this is something crazy, like handling disconnections at server side. Okay, and how to handle the offline users. So this is all we learned about the online. So online users have an active connection which is maintained by the connection gateway layer. The requests are handled in asynchronous non-blocking way, and there are specific languages and frameworks used for handling so many concurrent connections, and we need some specific mechanisms to handle disconnections on the server side. This is great. uh, so much to learn just from a very simple looking problem which is apparently not so simple looking. But yeah, how do you handle the offline users? Okay. Yeah, notifications. So when the user is offline, we should achieve two targets. One is notifications and one is sync when they return the mailbox button and push notifications. So the signaling, third party push notification. Okay, and then there is the nuance of so cold mode. So OS specific nuances of push notifications. So we have, yeah, in iPhones, I guess you need to do something differently. I am not so sure, but okay, this is an interesting thing to understand, like how it works. When a message arrives at a backend. So, okay. Yeah, this is, I think, important point here, that we need to also maintain whether a user is connected or not somewhere, so that we can persist those messages on our side, or we can check. So we can check when do we deliver the message. Okay, so when the message arrives at a, so when the message comes from user A to user B, and we notice that user B is not connected by checking on some session store. So the question here is, why use Redis as session store? It has mentioned about it, so I'll just try to ask it quickly. And user B is not connected to gateway, we switch to offline path. Okay, separate worker queue dedicated to push notifications. We package a small payload. Containing message message I need to, okay. Okay. Okay, so they're sent to some queue. So yeah, I do not still understand what is the cold path. So user is not connected. They are put into the queue. Makes sense. And then they are picked up by the servers or the app push notification services to be delivered to the users. So the question is, right, do we have separate how this queuing mechanism works when user is offline? Yeah, this is something that I don't completely understand. Okay, the sync and the mailbox, the delta sync, what is it? Maybe it will be clarified in here. Okay, so there seems to be some file descriptors or the message ID, some kind of thing. So they are maintaining, so the state of a user is maintained on the client as well as on the servers. So when a message is sent, a message ID is stored on the server, but then a catch up request is made when the user's device connects, and then you are able to fetch for the particular user for all the messages that happened after particular message ID. I think this might also play some role, this message ID, how these are guaranteed, how these are perform how these are created would also play some role in ordering of the messages as well. So let's just ask these questions, and how are these messages ensured to be ordered, right? So let's just ask these three questions before we finish our session for today. But I think we already have to some extent answer to this question. The I think more in-depth questions are what kind of database would you use and all those kind of things. Session storage is essentially global real-time phone book of your infrastructure. Okay, this is very interesting. So Redis provides us three features due to which we can use it to maintain the active sessions. The first is the latency, where you can perform large number of operations on it because it's in memory and not on the disk. So you perform the operations on RAM. Then the data structures are very simple, and we basically have a key value store that we can use to maintain the states without performing any complex queries. And let me pause this timer. And then we have the native TTL support. Like if you don't get any updates from a user, then you can automatically clean up using the using this feature of Redis. That totally makes sense. So it makes us think like what are the things that we need to kind of take care of while managing the users, right? High performance, low latency, and TTL, automatic purging. How does the mechanism work when the user is offline? We established that when the Redis says user is offline, two paths, okay? Queuing mechanism, signaling path. And it is crucial to decouple our fast internal system from the slow external mechanisms. The fork in the root is user page, okay, nil offline, the mailbox deposit before doing this. So my question is, does the message remain in queue even and retried? Offline. So what they're essentially saying is that, yeah, if we figure out the fork, right, if the user is connected or not, the mailbox deposit, before we do anything else, the message must be secured, okay? The offline user's message is written. Oh, I think I understand. Okay, so in case when the user is offline, we don't even put the message into the queue, and then we just directly, when the user will become online, then it will directly fetch. But if we realize that the user is online, then we would put the message into the job queue, and then it would be picked by the signaling services, and then the async worker would pull those messages from the queue and try to use whatever user's registered device is using that server to handle the payload. Okay, that totally makes sense. So two questions are answered. So there is no queuing mechanism when the user is offline, and how the message are ensured going to run. Okay, yeah. So as I expected, we are using monotonically increasing sequence IDs, often called the logical clocks. Okay, Snowflake approach. We don't use central database counter to generate IDs because at millions, that database becomes a red bottleneck. Okay, so you cannot use just the auto increment kind of approach because, yeah, how do you handle millions of messages per second and your database just dies? You have ULID and Snowflake mechanisms. Okay. So this is, I think, another interesting topic to discuss. Like, what is Snowflake ID? We will dive into this topic in a separate session. So, as this week we are discussing all about the real-time messaging apps. So, make sure you are subscribed to my channel. I'll see you in the next one.